Hello, everyone. Welcome to the ILTA Physics online problem solving lecture. Today, we are going to study Newton's law of universal gravitation. This law is a very important physical law that can explain not only an apple falling downward, but also the motion of celestial bodies in the universe. This illustration shows the very famous anecdote about Newton and the apple. It is said that Newton came up with the law of attraction, where objects pull on each other, after watching an apple fall from an apple tree. In other words, gravity, which is the attractive force between two objects, is an invisible yet powerful force that holds our universe together. The problems we will solve today cover the concepts of Newton's law of universal gravitation, as well as how to use it to calculate the free fall acceleration or gravitational acceleration on any given planet. Now, let's briefly summarize Newton's law of universal gravitation. Newton's law of gravity states that an attractive force acts between all objects that exist in the universe. This force is inversely proportional to the square of the distance between the two objects and directly proportional to the product of their masses. Also, these two forces act as an action-reaction pair, meaning they have the same magnitude but point in opposite directions. Let's explain this with a quantitative formula. The force that object 1 exerts on object 2, which we can call F sub 1 on 2, is equal in magnitude to the attractive force that object 2 exerts on object 1, which we can call F sub 2 on 1. This force can be expressed as the universal gravitational constant times the product of the masses of the two objects, divided by the square of the distance between them. At this time, the proportionality constant, which is the universal gravitational constant, is 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared. It is an extremely small constant. By using this law of attraction between objects, we can calculate the free fall acceleration on any given planet, which we commonly call the acceleration due to gravity. As shown in the diagram on the right, let's assume there is a planet with a radius of r sub p and a mass of m sub p, and there is an object with a mass of m at a height of h above the surface. Then we can analyze the force acting on this object from two different perspectives. The first perspective is the attractive force acting between the large planet and the small object, just like the law of universal gravitation we just explained. According to the formula, this force is expressed as the universal gravitational constant times the mass of the planet times the mass of the object divided by the quantity r sub p plus h squared, where r sub p plus h is the distance from the center of the planet to the object. However, since the height h is generally very small compared to the radius of the planet, we can approximate it by dropping the height h and just using the planet's radius. The second perspective is that, according to Newton's second law, there is a force pulling this object downward toward the planet, which is its weight. The weight we are familiar with is expressed as the product of the object's mass and the gravitational acceleration of that planet. In the end, these two forces are actually the exact same force looked at from two different points of view. Therefore, if we set force number 1 equal to force number 2 and solve for the acceleration due to gravity, we can get the following formula. So, if we know the mass and the radius of any given planet, we can calculate its gravitational acceleration using this formula. All right. Now let's solve some basic types of problems using the law of universal gravitation together. Problem number 35 is the most basic type of problem applying the law of universal gravitation. It says there is a star in space, and this star is twice as far from planet 2 as it is from planet 1. Also, the mass of planet 2 is twice the mass of planet 1. The question is asking for the ratio of the forces that each planet exerts on this star. We can easily explain this using the formula for Newton's law of universal gravitation that we already know. First of all, since the problem does not give us any quantitative numerical values as conditions, we need to represent appropriate values using variables. Let's set the distance between planet 1 and the star as r, the mass of planet 1 as lowercase m, and the mass of the star as capital M. Since we express the distance and mass of planet 1 as variables, the distance between planet 2 and the star becomes 2r, and the mass of planet 2 becomes 2m. Now, let's calculate each force using the formula for universal gravitation. The force that planet 1 exerts to pull the star can be expressed, according to the law of universal gravitation, as the gravitational constant g times the mass of planet 1 lowercase m times the mass of the star capital M divided by r squared. If we calculate the force exerted by planet 2 in the same way, the mass is twice as much and the distance is also twice as much. So when we calculate it, it turns out to be half of the force from planet 1. Therefore, the ratio of the two forces is 1/2. This is a very simple type of problem once you apply the formula. Please practice reading the problem and accurately expressing the conditions as mathematical formulas. Problem number 38 is a problem that can be solved by using both the law of universal gravitation and Newton's law of acceleration. It asks how much thrust needs to be produced by the rocket for Apollo 12 to land safely on the moon with an acceleration of 0. Here, the key condition of the problem is that the acceleration is 0. According to Newton's second law, for the acceleration to be 0, the net force acting on this object must be 0. If we draw this on a free body diagram, the Apollo 12 spacecraft that is landing experiences a downward gravitational force pulled by the moon and an upward thrust produced by the rocket. The case where the net force becomes 0 is when these two forces are equal in magnitude and opposite in direction. In other words, the upward thrust and the downward gravitational force must be equal. Specific parameters for the moon are not specified in the problem statement here, but in an actual test, they will be given in some form. They might give you the moon's gravitational acceleration directly, or they might give you the mass and radius of the moon. If the problem directly provides the value of the moon's gravitational acceleration, we can solve this problem with a simple equation like this. Due to the condition that the acceleration is 0, the thrust of the spacecraft becomes equal to its weight being pulled by gravity. If we calculate the weight of the spacecraft as the mass of the spacecraft times the gravitational acceleration of the moon, we get 1170 newtons. However, even if they do not give us the gravitational acceleration directly, but give us the mass and radius of the moon instead, we can still calculate the gravitational acceleration ourselves. As we learned earlier, the gravitational acceleration on any planet can be calculated using the formula. By plugging the values from the conditions into the formula, we can find the moon's gravitational acceleration. After that, since the thrust and weight are equal due to the 0 acceleration condition, solving it that way will give us the exact same force value. Today we solved some simple, basic types of problems using the law of universal gravitation. That's it for today's lecture. You all did a great job. See you next time.